terms of graph theory and combinatorics. Before we jump into some math, we'll first talk about what graph theory and combinatorics are, and what I spent my last semester and a half studying some of the topics which we'll cover today, and some I chose to leave out. So graph theory is a branch of mathematics studying relationships between objects represented by vertices, also called nodes or points, connected by edges, also called lines. Some topics I covered in my studies that we will cover today are isomorphisms, trees and forests, Euler and Hamiltonian paths and circuits, independence matching, and network flow theory. Some topics we'll cover today are a few types of graphs, namely complete, bipartite, and planar, and the vertex and edge colorings of each one. And combinatorics is a branch of mathematics focused on counting, arranging, and selecting finite discrete structures. Some topics covered, most of which we'll look at today, are permutations, combinations, distributions, partitions, and a few special counting methods such as inclusion, exclusion, recurrence relations, and generating functions. Today we'll focus on a variety of these combinatoric methods and using different ones to solve the same question. So a few definitions starting for graph theory. A graph consists of points which are called vertices in the singular is vertex, and connections called edges. A vertex is a point, and ones that are joined by the same edge are called adjacent vertices. So for example, vertices 1 and 2 are considered to be adjacent because they share an edge. The degree is the number of edges that occur at a single point. So for example, vertice 1 has degree 3 because there's 3 edges that come out of that point. An edge is the connection between vertices, indicated by line segments and curved lines. And a connected graph is where a path exists between all of the pairs of vertices. So that top graph with the vertices 1 through 5 is considered to be connected because you can get from 1 to 5, 3 to 2, and that bottom portion is also connected because you can get from 7 to 8 and 8 to 6. But if you were to combine those two components, they would not be connected because you can't get from 1 to 6 in that graph because there's no edges connecting between those vertices. We'll jump into some key graph types, and we'll start with complete graphs, which is where all of the vertices are adjacent to each other, and this is denoted in case of n with n vertices, where every vertex has the degree of n minus 1. So the graph on that bottom left is a K5 graph, and if you, all of the vertices have degree of n minus 1 because other than the vertex you're referring to, all of the other vertices are connected to it. So that K5 will have degree 4, and that K4 on the right will have degree 3 because it has one less vertex. And then we have bipartite graphs, which those vertices can be divided into two sets, normally denoted x and y, but you can choose whatever. And this is where every edge in the graph has one endpoint in each of those sets. And because of that trait, bipartite graphs are what are called two-colorable, meaning each vertex can be assigned one of two colors, so that each edge in the graph has one endpoint of each color. Combining those two, we have complete bipartite graphs, which is where every vertex is in x is adjacent to every vertex in y, and these are denoted k, m, n, where m and n are the vertices in x and y respectively. And so the image that we have here is a K4, 3, and the vertice degrees are opposite. So those 4 vertices at the top will have degree 3 because they're connected to all 3 of those at the bottom, and those 3 at the bottom will have degree 4 because they're connected to all 4 at the top. And since it is still bipartite, it still is two-colorable. And finally, our last key graph type is a planar graph, which is a graph that can be represented by a diagram in which no edges cross. But it doesn't have to appear that way, though. These two graphs are actually the exact same. It just, the one on the right is an unfolded version of the one on the left. But if you looked at the one on the left, you wouldn't think it's a planar graph by just looking at it. Planar graphs have what are called regions, and one of which is the infinite outer region. But another way to look at that is the number of faces that this graph has. And so the graph on the right has 3 regions, so it has those 2 smaller triangles and then that big outside outer triangle. We can check if a graph is planar by using what's called Euler's formula, which says that if G is a connected planar graph with V vertices E edges in R regions, then V minus E plus R is equal to 2. And so for our graph, we have 5 vertices and 6 edges in 3 regions, so 5 minus 6 is negative 1, plus 3 is 2, which shows that the graph is planar. Now that we have our key graph types, we can move to coloring those vertices. And we'll start with some definitions again. A proper vertex coloring is an assignment of a color to each vertex of a graph so that no color occurs in adjacent vertices. And a minimal proper vertex coloring is just coloring, or having a proper vertex coloring with the smallest number of colors possible. And the chromatic number chi is just the number of colors that occur in that minimal proper vertex coloring. So in our photos, the image on the left is a proper vertex coloring because none of those adjacent vertices have the repeating color, but the one on the right is minimal because we used the fewest number of colors possible. We have a few theorems associated with our key graph types that we discussed. In vertex coloring theorem number 2 says that for every graph, chi is less than or equal to the maximum degree plus 1. So all this is saying is that we'll never need more than the maximum degree plus 1 colors to color the vertices in any graph. And so this picture, that purple vertice towards the left-hand side has a degree of 5. And so all that theorem is saying is that we'll never need more than 6 colors to properly color those vertices, but we actually only needed 3. Another theorem is vertex coloring theorem number 4, which is also called the 4-color theorem. And this says that for every planar graph, chi is less than or equal to 4. And so for this planar graph, we actually only needed 3 colors to color those vertices properly. Based off of our theorems and what we know about our key graph types, we can come to a few conclusions. So for complete graphs, they have a chi of n for n vertices, and this is because a proper vertex coloring requires that no adjacent vertices can have repeating colors, and since complete graphs have the vertices are all adjacent to each other, they're going to each have to have their own color. And as we mentioned earlier, bipartite graphs and complete bipartite graphs are 2-colorable, which means they have a chi of 2. And based on that 4-color theorem, our planar graphs have a chi of 4, and that bottom right-hand graph is a planar graph, and we needed 4 colors to properly color that. Now that we've colored the vertices, we can color the edges, and the definitions are relatively similar to those of vertex coloring, but just changed slightly because they're edges, not vertices. So a proper edge coloring is an assignment of a color to each edge of the graph, so that no color occurs on edges that share a common endpoint. And a minimal proper edge coloring is just the proper edge coloring with the smallest number of colors possible. And the chromatic index chi prime is the number of colors that occur for that minimal proper edge coloring. So again, that left-hand graph is a proper edge coloring because none of those vertices have more than one edge that's the same color. But that right-hand graph is a minimal proper edge coloring because we used the fewest number of colors possible to color those edges. Like we had for vertex coloring, there's a few theorems that apply to our key graph types. The first of which is edge coloring theorem number 2, which says that in any graph with maximum degree delta, the edge coloring is either class 1, which is delta, or class 2, which is delta plus 1. And so again, this is similar to that other edge coloring theorem. We'll only need a maximum of delta plus 1 colors to properly color those edges, but we can classify them 2 ways. And so this picture, if you look at vertex 8, it has a degree of 5, so we would most need 6 colors to properly color those edges, but we only needed 5, making it a class 1. Then our second edge coloring theorem is edge coloring theorem number 3, which says that in any bipartite graph with maximum degree, our chi prime is equal to delta. And so if you look at vertex 5, we have a degree of 3, and we needed 3 colors to properly color that bipartite graph. Again, just like our vertex coloring, we can come to a few conclusions. A complete graph is class 1 when our chi prime, complete graphs are class 1 when our n is even, and complete graphs are class 2 when n is odd. So that bottom left-hand graph is a K5 graph, so n is odd, so we'll need our delta plus 1 to properly color those, and a delta for a K5 graph, remember, is 4, so we'll need 5 colors to properly color that graph. And then that graph on the right is a K6, and since the vertice count is even, we'll just need the maximum vertex count, or maximum the degree for each color, so we'll need 5 for that one. So even though those graphs look pretty different, we needed the same number of colors to properly color those edges. For the bipartite graphs, as we said with that theorem, our chi prime is our maximum vertex degree. And similarly for our complete bipartite graphs, however, since those have 2 sets of vertices, it's just whichever set has the larger number of vertices, that is what your chi prime is going to be. So for that K4-3 graph on that bottom right, since those 3 bottom vertices have 4 edges going into them, it'll be a chi prime of 4. And finally, our planar graphs. There's not a specific theorem applying to planar graphs that our textbook covered, but they just said that most are class 1, and this graph here is a planar graph, and vertex 4 has a degree of 5, and we only needed 5 colors, which it also means is class 1. Now that we've colored our edges and vertices, we can move to the second part of my honors project, which is combinatorics, and we'll start with a few definitions before jumping into some math. So a permutation is an arrangement of all the elements of a set in a particular order without repetition, and order does matter. A combination is a list of elements when the order of elements is not taken into account. A distribution is an assignment of a set of objects into a number of different locations, and a partition is how many ways can a set be separated into a number of different sections. And we have a few special counting methods we'll talk about today, which is inclusion and exclusion, which is a counting method used to find the size of a union of overlapping sets by adding and subtracting overlaps so that nothing is counted more than once. And finally, generating functions are polynomials or infinite series constructed in such a way that the coefficients provide answers to combinatorial problems. Starting with permutations, again, order matters when you can't have repetition, so we're finding the number of orders of a set of items. And the generic formula for permutations is n factorial divided by n minus k factorial for n items and k length. So if we want to find the number of permutations of the set 0 through 9 with 10 items, we would just have 10 factorial because we have 10 options for that first number, 9 for the second, 8 for the third, and so on. But if we change the problem slightly, and we want to permute that set of 10 items, but we only want it to be length 4, there's two ways that we can approach this. We can do it kind of what we did with factorial, but we only choose the first 4 values for that, since we have 10 options for the first one, 9 for the second, 8 for the third, and 7 for the fourth. Or we can use our permutation formula, which we could have done for the first one, but it's kind of redundant when you're just permuting something that's the same number of sets in that, or same number of objects in that set. But we can plug in our 10 factorial divided by 10 minus 4 factorial, and if you multiply that out and simplify, you get the same number. Moving on to combinations. Again, order doesn't matter for combinations, so like ABC is the same thing as CBA with combinations. So if we want to find the number of 5-element combinations without repetition from a set of 10 elements, we can start by taking our first 5 values like we would with a permutation. So we'll have 10 times 9 times 8 times 7 times 6. And since there's 5 factorial ways that we can rotate those objects, and we don't care about the order with combinations, we can divide our total, that 10 times 9, all the way up to 6. We can divide that by that 5 factorial to get 252. But there is a generic formula that we can use for combinations, and that's similar to our permutation one. You'll take your n factorial divided by k factorial times that n minus k factorial, which everything except that k factorial portion is the exact same thing as that permutation formula, but we're just dividing by the number of ways that we can rearrange that set that we chose, and that is denoted n choose k. Moving on to distributions, which combines permutation and combination techniques to find the number of ways to put objects in places. So if we want to find the number of ways to distribute 5 different colored balls into 4 distinct boxes, each distinct ball has 4 options for those boxes. So if you have a red ball, you have 4 options for that one, and then if you have a green one, you also have 4 options. So for those 5 balls, you'll have 4 to the 5th. But if we change the problem slightly and indicate that all of the balls are the same, this changes the problem drastically. We use dividers to indicate boxes, and we're looking at, since the balls are the same and the boxes are the same, we're looking at how to, or the boxes are like their own individual box, but the lines indicate boxes where the spaces on the left and the right hand side of the last 2 are the boxes. There's not an extra line indicating boxes, but we're looking at how to put 8 items into a row. And so we can either do 8 choose 3 for those 3 lines indicating those boxes, or we can do 8 choose 5 for the 5 balls. Those actually are equivalent. So for distributing our 5 identical balls into 4 boxes, we get 8 choose 3. And this is called the stars and bars formula, which allows for empty boxes, which is that first formula on the bottom. And like I said, we can either use our n for balls or the n minus 1 for those boxes, and they're actually equivalent. And then we can also change the problem slightly. And if we indicate that no box can be empty, then it changes it so we have n minus 1 choose n minus 1 if we want no box to be empty. And then we have our last regular combination or combinatorial method, and that's partitions. So we want to find the number of ways a class of 25 students can be divided into groups of 5. And so we'll have 25 choose 5 for that first group, and then we'll do 20 choose 5, 15 choose 5, and 10 choose 5. 5 choose 5 is just 1, so it's just multiplying by 1. And then we can divide by that 5 factorial to get rid of the permutations of those groups, kind of what we did for that combination example. But we can generalize this to find the number of partitions of a certain number of sets. So if we have a 15-element set, and we want to partition it into 5 sets of 3. We'll have our multinomial, which is that top numerator portion, which is 15 factorial divided by 3 factorial to the 5th, and then we'll divide that by 5 factorial as well, because there's 5 of the same type of partition. And for the second one, the type 1, 2, 3, 4, and 5, our multinomial will be 15 factorial divided by 1 factorial times 2 factorial all the way up to 5 factorial for those each different types of partitions. And then that will also be divided by 1 factorial because none of those partition types are the same as one another. So if we had 2 2s, we would divide by 2 factorial because we have 2 of the same kind. Moving on to our special counting methods, we have inclusion exclusion, which again finds the union of overlapping sets by adding and subtracting overlap so that nothing is counted more than once. And so the general pattern of this is adding the singles together, subtracting the doubles, adding back the triples, and subtracting out the quadruples. And so you'll continue this as signs alternate, so the union equals the addition and subtraction of those intersections. So for counting, you'll take the total number of possibilities, subtract out case 1, and add back case 2, and keep going as much as you need to. And so if we want to find the number of ways to distribute 3 red balls, 4 blue balls, and 5 green balls into 4 distinct boxes with no empty boxes, we'll start with the total distributions, distributing the identical balls into the distinct boxes for each other, for each color, and then multiply those together. We'll use the stars and bars formula, which allows for empty boxes, which our problem says, no, we don't want empty boxes, but this is a key part of that inclusion exclusion formula, is by adding and subtracting all those out, it'll remove the empty boxes. So for that first one on that top left, we have 6 choose 3, which is those 3 red balls, plus 4 boxes minus 1, choose the 4 boxes minus 1, and then we'll do the same thing for the blue and the green balls, multiply all those together. And then to the right of that, we have 5 choose 2, so we'll have our 3 red balls plus the 3 boxes minus 1, choose the 3 boxes minus 1, multiply all those together, and then we have to choose which box is empty. So that's that 4 choose 1, and we'll multiply that by that. And then for our bottom left, that is, we have 2 boxes empty, so we'll subtract out 2 from the top and bottom portion for that left-hand side, and then multiply by 4 choose 2 for those 2 boxes empty. And then for 3 boxes empty, we're just choosing which box has all of the balls or which boxes don't have any of them. So that's just 4 choose 3. So then we'll start with our total, which is that 39,200 number. Subtract out the 12,600 number, add back the 2 boxes empty, which is 720, and then subtract out 4. And then we get our 27,316 different ways that we can distribute those different colored balls into those boxes. And finally, we have generating functions. And these are polynomials constructed in a way that the coefficients provide answers to combinatorial problems. So if we're given the question, if we want to find the number of ways nickels, dimes, and quarters add up to 50 cents, we'll set up the generating function first by looking at the different kinds of coins and how many it takes to add up to that desired amount. So for quarters, we can have either 0 quarters, which is what that 1 indicates, and then we can have 1 or 2, and then similarly for dimes and nickels, we can have 1 up to 5 dimes or 0 and up to 10 nickels. And so we can start out this way by kind of just visualizing what we're looking for, and then we want to find a common variable so that when we multiply these together, it's easier for us. So we'll plug in x with the exponent of what the coin value is worth. So for quarters, we'll leave 1 because there's 0 quarters for that, and then 1 quarter will be x to the 25th because they're worth 25 cents, and then 2 quarters will be x to the 50. And then you'll repeat that for both dimes and nickels, and you'll multiply all those together like you would any other polynomial. The key here is we're looking for the coefficient on the x to the 50 term because that's what the 50 cents is we're looking for. And we find that after multiplying all those polynomials together, is the coefficient on the x to the 50 term is 10, which tells us that there's 10 combinations of nickels, dimes, and quarters that will add up to 50 cents. Now that we've looked at a variety of different combinatorial methods, we can use a few of them to solve the same question. So for given the question, distribute 10 identical balls into 4 boxes with no box empty, you can use a combinatorial formula, inclusion, exclusion, and a generating function. So we can start with the formula from our distribution slide. Remember the n-1, choose n-1 for that no box empty. So we'll plug in our 10 and 4 to get 9, choose 3, which is 84. But then if we go to inclusion, exclusion, it's a little bit more labor intensive. So if we use our formula, the key is here we'll start with stars and bars, which allows for empty boxes. So then we'll plug in our 4 plus 10 minus 1, choose 10, and we're using the formula that is choosing the number of balls rather than the number of dividers, but like I said earlier, they're equivalent, so it doesn't really matter which one you choose. And so we'll get 13 choose 10 for that total number, and then if we choose one empty, we have that 3 plus 10 minus 1, choose 10, and then we'll have to multiply by 4, choose 1 to choose that one box empty, and then we'll do the same thing for 2 and 3 empty that we did for our other inclusion and exclusion problem. So we'll get 286 minus 264, 66 minus 4 is 84, which matches what we got with that combinatorial problem. And finally, with generating functions, since each box must have one ball because we can't have any boxes empty, we won't have a 1 indicating 0 balls. We also don't really need x to the 10th either, because that would mean that all of the balls are in one box, which would create empty boxes, but it's there for a visual purpose. So for each box, we'll have x plus x squared all the way up to x to the 10th, and then we'll have that to the 4th power because there's 4 boxes. So if we were to multiply that out like any other polynomial, we're looking for the coefficient on x to the 10th, because that's where the 10, or how many ways you can distribute those 10 balls. And after multiplying that out, we find that the coefficient is 84, which matches the other two that we got. This shows that for given a single problem, you can use a variety of different methods, some of which are clearly easier and less labor intensive than others, like the formula rather than generating functions. So today, we looked at a few types of graphs, and we looked at the vertex and edge coloring of each one. We solved a variety of problems with combinatorial methods and saw that many methods can be used to solve the same problem. These methods can be used to solve everyday problems you come across all the time, like seating your friends at a table. How many outfits can you make with the number of socks, shirts, and pants that you have? Or if you have a bunch of nickels, dimes, and quarters, how many ways can you make 75 cents or $1.50 with those? With your new information on graph theory and combinatorics, look for coloring and counting opportunities in your everyday life and apply some mathematical techniques.